Hi everyone, welcome to our next video for week 6, where we're going to talk about tests of independence. So these tests that we're going to talk about in video 3 and video 4 are tests using contingency tables. When data can be tabulated in table form in terms of frequencies, several types of hypothesis tests can be tested using the chi-squared test and the chi-squared distribution. A test of independence of variables is used to determine whether two variables are independent of or related to each other when a single sample is selected. And a test for homogeneity of proportions is used to determine whether the proportions for a variable are equal when several samples are selected from different populations. So this video is focusing on a test for independence. And the chi-squared goodness of fit test can be used to test the independence of two variables. We are lucky in that the TI-84 has evolved in that it has a separate chi-squared test for tests for independence and homogeneity. GeoGebra uses the same function call for all three, goodness of fit, independence, and homogeneity. It's just going to ask for different pieces of information. So all three of the tests we're talking about that involve data tables are related and very similar. Step one, we're stating hypotheses. For tests of independence, the assumption is that the two variables are independent. There is no relationship between the two variables. The alternative is then that the variables are dependent. There is a relationship between the variables. This is going to be true for every test for independence. The only thing that's going to change is the two variables that we're comparing. If the null hypothesis is rejected, then there is some relationship between the two variables that we're comparing. When data are arranged in table form for a test for independence or a test for homogeneity of proportions, the table is called a contingency table. And basically what a contingency table does is it splits up data into two different variables. So the column labels represent the categories for one variable, like hair color, and the row titles represent the categories of a second variable. I can't remember what I said, hair color and eye color. We saw a chart very similar to that a few weeks ago. You will notice here that we've labeled each of those boxes. So this first box here, row 1, column 1, is C11. Row 1, column 2 is C12. So when we label each cell in a contingency table, we label it with the row and then the column. So row 2, column 3 would be C23. Row 2, column 1 would be C21. We're going to use that to refer a little bit to cells in the table. The upside is this becomes less important when we use technology. This type of notation is super important if you're doing these tests by hand, but we're not going to be doing that. The degrees of freedom for these contingency table tests, both independence and homogeneity, which is the next video, are the number of rows minus 1 times the number of columns minus 1. So in this particular example, we have 3 columns and 2 rows. So 2 minus 1 is 1, and 3 minus 1 is 2. 1 times 2 is 2. So the degrees of freedom for this contingency table would be 2. Unless you have a very large contingency table, meaning you're comparing variables that have a lot of possible categories, those degrees of freedom are typically going to be fairly small. In order to test the null hypothesis, we have to compute the expected frequencies, assuming the null hypothesis is true. So we're going to be given a contingency table that has sample data in it. We then need to calculate expected frequencies, assuming that those two variables are independent. There is a formula for this. So to calculate the expected value for each cell in your contingency table, you take the row sum times the column sum and divide it by the grand total, the overall sample size. This means for a table like we saw in the previous slide that had 3 rows and 2 columns, that means there were 6 cells. We'd have to do 6 different expected frequency calculations. So for cell 1, 2, so row 1, column 2, I would do the row 1 total times the column 2 total divided by the total sample size. If you are calculating this by hand, you should add the expected values to the original contingency table in parentheses. And you would do this as a first step before you start your hypothesis test. So let's go back to that slide. These C11, C12, C13s all represent observed data. You would then calculate by hand an expected value, and you would write it in each box in parentheses next to the observed value. You can see just me labeling this starts to feel a little bit tedious, which is why you should be very glad that you live in 2023 and you are not going to have to do this. And that's because modern calculators will do this formula for you. Because this formula depends on information that you can pull from the sample data, that row total you pull from the sample data, column total you pull from the sample data, grand total, you just add up all the sample data. The calculator can do these calculations in the background. So for these tests that we're running with contingency tables, you're going to feed in only the observed data, and the calculator is going to calculate the expected frequencies for you. So let's talk about how to calculate the p-value for this type of test. If you're on a TI-84, you're going to go to a new menu, which is the matrix menu. So let me pull up my TI-84 real quick. So here's my TI-84. And when you press second chi-squared, or not second chi-squared, second x to the -1, you pull up the matrix menu. You can see in blue above that x to the -1 button, we have matrix. And it has 3 options, names, math, edit. We want to go to edit, which is going to allow us to enter our observed data. So you go over to edit and you hit enter, because generally we want to edit that first matrix because that's the default our calculator is going to assume we're editing. And then you enter the number of columns and rows in your table. So for example, we had 3 columns, enter, and then 2 rows. Ooh, and that's backwards. You'll notice that gives us 3 rows, 2 columns. So we want to do it backwards. It want rows first and then columns. So 2 rows, 3 columns, and you enter those observed frequencies in that table. To do that, you type a number and then you press enter, and it'll take you to the next spot. Type a number, press enter, type a number, press enter. And that's basically it. You're done editing your matrix, and you can move on to the next step. If we wanted to run a chi-square test on this, we would go stat, test, and down to option C, which is just chi-squared test. And this is the test we're going to use for tests for independence and tests for homogeneity. And you'll notice it provides spots for observed and expected. You only need to enter observed. The calculator is going to put the expected in that second matrix on its own. So as long as we put something in A, we're good to go. We press calculate and it spits out a p-value for us. So hopefully not too scary. GeoGebra is very similar. It just wants a matrix of the observed values. The difference is you can't get a matrix on the screen in the same way that you saw on the TI. So in this case, you're basically going to create a list of lists. So let's pull up GeoGebra and take a look at what that would look like. So let's clear out some of our data from that last video. And I'm going to enter that same information I put in the TI-84. So I had two lists, two rows rather, 1, 2, 3, and 4, 5, 6. So I'm going to call my matrix M, and the outer brackets are for the whole matrix. And then I want a list for the first row, 1, 2, 3. And then I want to go outside that, comma, and then the second list for the second row, 4, 5, 6. And you'll notice it spits it out in matrix form. I just can't enter it that way. So next, we're going to do that function call, chi-squared test. And I'm going to feed it just a matrix, just that M. And you'll notice it spits out that same p-value that the TI-84 did. So it is a little bit more tedious to get the data into the calculator, but once it's in the calculator, the function call is fairly straightforward. Just like last time, we're going to do 2 examples. So first example is 11.6 from your book, and it says, in a volunteer group, adults 21 and older volunteer from 1 to 9 hours each week to spend time with a disabled senior citizen. The program recruits among community college students, four-year college students, and non-students. In the table below is a sample of the adult volunteers and the number of hours they volunteer per week. Is the number of hours volunteered independent of the type of volunteer? So they're asking us, is there a relationship between the type of volunteer, community college, four-year college, or not a student, and the number of hours they spend volunteering? So let's go ahead and pull up our whiteboard again so we have some space to write. We're going to go ahead and pick off some information here. Get my pen going. First, you'll notice in that question, they use the word independent, and then they identified 2 variables, number of hours volunteered and type of volunteer. So that's a really good clue that I'm performing a test of independence. They're asking about the dependence or the relationship between 2 distinct variables. The fact that I'm given a contingency table is also a really good clue. I know when I'm given that contingency table that this is sample data. So this is from 839 volunteer adults 21 or older. So this is the information that needs to go in the matrix minus the row and column total. All the computer needs is the actual raw data, these boxes in white in the middle of the table. And we can see for our 2 variables, number of hours volunteered, our categories are 1 to 3, 4 to 6, 7 to 9. And then types of volunteers are the types of students, community college, 4-year or non. We don't have to calculate our expected values, but we should figure out our degrees of freedom. That's just good practice. And we know that that's rows minus 1 times columns minus 1. So in this case, we have 3 rows, 3 types of volunteers, and we have 3 columns, 3 different hour brackets. 3 minus 1 is 2, 2 times 2 is 4. So for this test, our degrees of freedom is 4. You will notice that GeoGebra and the TI-84, when we went through those functions in the last slide, didn't ask for that because it can figure that out from the size of the matrix we feed it. So your calculator is doing what we just did here in the background. Okay, let's jump into our 4-step hypothesis test. Step 1, identify your hypotheses and your claim. The null is number of hours and type of volunteer are independent. No relationship. And then the alternative is that they are dependent, that there is a relationship. In this case, it says, is the number of hours of volunteers independent of the type of volunteer? So they're telling me that my null is the claim that we are testing. So that's going to affect how we phrase our conclusion in step 4. For step 2, we're going to calculate our p-value. We know that we need to feed our observed values into a matrix. So if I'm doing this on GeoGebra, I would write that I put my observed into a matrix called M, and that my degrees of freedom is 4. And then I would call that function chi-squared test M. If I'm on a TI-84, it's going to ask me observed, which I'm going to put in matrix A because that's the default. It asks me where the expected should go. That defaults to B, and then degrees of freedom is 4. And that is chi-squared test. And it asks for both matrices, observed and expected, even though we're only filling in observed. So I'm going to go ahead and do this first example with the TI. So for the TI, the first thing, we enter that data in a matrix. So we're going to go second, x to the minus 1. We're going to go to edit. And this table is a 3 by 3. And then we're going to go down and just type that data. Oops, I guess it helps if I hit enter. I done messed up there, sorry. And we check that matrix should look like it does in the original data table. And it does. So next step, stat, test, chi-square test, which is option C. Observed is in A. We want the expected in B. We go down to calculate. And it spits out a p-value of 0.113. 0.113. So let me jot that down really quick, and then we're going to come back and look at our calculator. So we wanted that data, that expected data, the calculated values, assuming that these variables are independent, to go into matrix B. So let's take a look at what's in matrix B. So I just went second, x to the minus 1. I'm going to stay in names. I'm just going to go down to B and hit enter. and then enter again. And you can see that it spits out a matrix. So that first column is 90 point something, 103 point something, 104 point something. And you can scroll sideways to see the next few rows. So that calculator is really doing that in the background. Okay, let's go ahead and continue with our hypothesis test. Step 3, we compare our p-value to our alpha. And I don't see an alpha in this problem. It just says is the number of hours volunteered independent of the type of volunteer. And we know that when we're missing an alpha, we assume that it's 0.05. And I think that I mistyped that, but let me pull that calculator back up again. This is what happens when I don't have anyone to call me on my boo-boos. 0113, that makes more sense. There should be a 0 here. And 0113 is less than 0.5. So we should reject the null here. And then we know in step 4, when we reject the null, there is enough evidence. And then looking back at step 1, the null was the claim. So there is enough evidence to reject the claim that. The number of hours volunteered is independent of the type of volunteer. And that's wording we can pull right from that very last. So there is enough evidence to reject the claim that the number of hours volunteered is independent of the type of volunteer. So at least for this group, those two variables are dependent. There is a relationship between the number of hours volunteered and what type of student they are. Okay, let's go ahead and try another one. So this next example is pulled from a different stats book. It says a recent study of 100 individuals found the following living arrangements for men and women. The results are shown. Check the data for a dependent relationship at alpha equals 0.05. And then we can see in this table, they have 2 genders, men and women, and then 4 categories: living with a spouse, with a relative, with a non-relative, or alone. So we'll start the same way we did before. We know when we enter information, we can ignore the row and column totals. We only need those if we're calculating our expected values by hand. We should calculate our degrees of freedom really quick. So rows -1 times columns -1. In this case, we have 2 rows and 4 columns. So 2 minus 1 is 1, 4 minus 1 is 3, so that's going to be 3. Okay, the other information we were given here, alpha is 0.05, so they did give us a level of significance, and they said, check the data for a dependent relationship. So in this case, we are testing the alternative because we know that the null is independent. There is no relationship. So let's go ahead and do that first step. Null, no relationship. Relationships, the Marian spell, between gender and living arrangement. And then the alternative is the opposite. There is a dependent relationship. Dependent. then we already know they use that keyword dependent. So this is the claim that we are testing. Step 2, we're going to go ahead and do our p-value. So in this case, we know that we are putting our observed into, in this case, I'm going to do matrix A. And then I don't actually have to do an expected because this time I'm doing GeoGebra. So I really only need to know where that observed is and then what my degrees of freedom are. And then the GeoGebra function call is chi-squared test. And then the matrix name. So let's go ahead, pull GeoGebra up and run that really quick. So I called my matrix A. So A equals, and then my first row. Out of those curly brackets, comma, and then another set of curly brackets for the second row. And then when I hit enter, I should see a structure that looks like that data that's entered in those white boxes in the contingency table. And I do 57, 8, 25, 10 in the first row, 53, 5, 28, 14 in the second. So that's a good sign. And then we just run the function call, the chi-squared test A. And it spits out a p-value of 0.642. That's going to round to 7, so 6427. For step 3, we're going to compare that 6427 to our alpha value, which is 0.05. And 0.64 is much bigger than 0.05. So we're going to not reject. And then for step 4, since we did not reject, there is not enough evidence. And then looking at step 1, the alternative was the claim. So we talk about support. So there's not enough evidence to support the claim. And then for this problem, there is not enough evidence to support the claim that there is a dependent relationship between gender and living. Okay, so I'm hoping we feel pretty comfortable with that. If not, feel free to send any questions via email or to drop by office hours Tuesday, Thursday, Saturday. Otherwise, I will see you in the next video.